Hi everyone. Today we'll learn a buck converter control system using both fuzzy logic control and PID control. So first of all, we go to fuzzy toolbox. Here you can see there is input, output, and um, some rules. I have made a fuzzy logic tools, and I will import it. So from file I have a saved fuzzy logic file. Here there is two input, one is error and other is change of error, and this is output. So this input, if we see this, there is actually five membership functions called not big, not small, negative big, negative small, zero error, positive small, positive big. So I have generated it using a simple way. Here you can see, if I click NB, this there is parameter minus 1.5. This is a triangle. This triangle's base is here minus 1.5, and its peak is minus 1, so minus 1, and its other base is minus 0.5. So this is like this. If you write this, you will get this kind of shape. And not negative is small. Here if you select this, this minus 1, minus 0.50, minus 1, 0.50. So you got the idea how to generate this membership function. You can do this. I am showing you. This is Manmani Fuzzy. So you add a membership function. So here, this in this input you add, and there is three membership function. You can add some add membership function here. From here you can add another two membership functions. So here is our five membership functions, and you can select one membership function and define its shape by using this column. So this is 0 and 0.5, then 1. You can say it 1, then its shape has changed. So you got the idea how to change the shape, and you can select another and change its shape. And here there is range 0 to 1, but in my simulation I have used range minus 1 to plus 1. So here 0 to 1, here minus 1 to plus 1. So you can change it also. Display range you can change. So you got the idea now. There is two input. One input, first input is error, and second input is change of error, and they are same. I used the function, they are same. And there is output also contains five membership functions, and they are defined like this. The interesting point is that you have to add rules to this membership functions. Let me find it. So here you can see this is error, and this is change of error, and there is five membership function for error, and five membership function of change of error, and there is five membership function of output. Now when the error is not negative big and change of error is negative big, the output is negative big. Similarly, all other things are specified in a table. You can make this table, or you can get this table from a research paper. Okay, I got my table from a research paper. Unfortunately, I forgot where I saved the research paper. So this is not the research I am showing you. It is boost converter. I am not showing you boost converter, I am showing you buck converter. So here is, but the main thing is same. Don't overthink it. Now there, this is not mine. So this is my fuzzy logic designer block. Here there is input and input to error, change in error, and this is output. So after defining all the membership functions, we have to add a rules, or we have to add rules. So in the edit uh, toolbars, here you can find rules, click there, and here you will find input 1, there is 5, 1 2 3 4, and 5 1 2 3 4 5, and their input 2 is 5, 1 2 3 4 5, and output is 5. So like I have shown you, when input is negative big and input 2 is negative big, input 1 is error, input 2 is change in error, you will get the idea what is error and change in error in a minute. So when input 1 is negative big and input 2 is negative big, output is negative big. When input 1 is negative small, input 2 is negative big, output is what it will be defined by you. So here I have defined it, and added the rules. You can change the rules, delete the rules, play with it. So here in one, you can see if input is not negative big, input is negative big, that output is negative big. So there is actually 5 by 5, so 25 rules. Here you can see 25 rules, and all the rules will define the output according to the designer. It's up to you, you have to design it. Now after adding the rules, you need to save this. So you can export this to file or to workspace. If you export this to file, you will save this to your computer. If you export this to your workspace, then it will come to your workspace. So first of all, let us clear all of the things in my workspace. Clear all, there is nothing here. Okay, so there is nothing here. Now now open buck converter. Our this I have made from previously I have made it. It's very easy. I can show you how to make it. So there is this is a controlled voltage source. So take a controlled voltage source. Okay, this is control voltage. This is a MOSFET. So MOSFET, write it, you will get a MOSFET. This is also a MOSFET, and this is series RLC branch. So write series RLC branch, you will get it. There is three things. You will have to choose resistance and inductance. So RL branch, and apply it. So what is the parameter? Resistance is 0.001, inductance is like this. You have to put the value here, right value. Then there is resistance and capacitance. So click control and click here, you will copy it, control R. So you will rotate it here, click here, and select RC, and all the values of resistance and capacitance should be come here. Resistance is ato, capacitance is this. So you will find it. Then there is a controls current source. So controlled current source. Okay, so there is control current source. This is not control current source, are another controlled current source. This control current source you should take. There is also this is called voltage measurement. So voltage measurement, this thing, and all of these things. This is step. So step, take step. There this is gain. This block is called gain. So write gain, you will find gain block. Then this is sum block. So write sum. There is plus plus, so you need to select plus minus. So uh, minus plus, you will get the exact shape like this. This is a constant, so add write constant and find it. This is a saturation block, so saturation block, you will find this block. This is a memory, so add memory block here. Then there is, this is marks, so add marks. There this is fuzzy fuzzy logic toolbox, so you need to find fuzzy logic controller. So this is our fuzzy logic controller. This is input and this is output, so you have to give the input, and input should be given with the marks. Okay, and this is our triangle generator. So triangle generator, this is triangle generator. You will you can change this like this. And this is a relation block, so relation block, and all is there. So now I am showing you the things here. So this step is you can define this step. I have defined it 0 point step time is 0.05, initial value 12 volt, and final value 20 volt. That means when time is less than 0.05, then input voltage is 12 volt, and when time is greater than 0.05, input voltage is 20 volt. And this step will change the output current. So step time is 0.1, initial current is 5, and when time comes to 0.1, current will become 10 ampere. And this is my inductor with some resistance. So the resistance is this and inductance is this, and this is my capacitor, and here is series equivalent series resistance is this, and this is the capacitance. And also I don't need this. And this is a sum block, and this is my desired output voltage. I want to see, make the output voltage constant to 5 volt. So this is 5, this is negative feedback coming here, and then error signal is going through a gain. I will tell you about this gain block in a minute. And there is a saturation block, and saturation block will limit the output from +1 to -1. Why? Because the input of fuzzy logic controller, we defined the membership function, and the membership function is within the limit of +1 to -1. So we have to saturate the output of the error to +1 to -1. Otherwise, if it goes beyond this +1 or goes less than -1, then fuzzy logic controller can recognize the input. So this is the error, this is error, and this is change in error. So error, and then error is going through a memory block, and this memory block will store the value of previous error, and this is the most recent error, and this is the difference of the two error. So this is change in error. So this is two inputs, one input is error, in the other input is change in error. So I have told you about this thing. There is two input, one is error, this is error, and there is this membership function, it is -1 to +1. So we have used the saturation block, and there is the change in error, and in this change in error there is the membership function which is within the range of +1 to -1, and output also within the range of +1 to -1. Input 1 is error, and input 2 is change in error. So these two will be given to this fuzzy logic controller. Now in this fuzzy logic controller, if you double click it, I have given the fuzzy fish name bug fish. I saved this file as name as bug fish, so I use the same name. Okay, and there is this triangular generator, and this triangular generator is starting from -1 to +1. So it is +1 -1, and you have to put phase 180° to get this kind of shape. And the frequency, the converter frequency is 25 kilohertz. It's very high frequency. and there is this relation block, and this relation block is working to generate a PWM when this output is greater than this, then output will be high, and this this fuzzy logic output is if the fuzzy logic output is lower than this value, then the output will be low. So and there is this not gate. This not gate will complement this signal, because this is a synchronous buck converter. So if this is on, this should be off. This is, if this is on, this should be off. So I think you got all of these things now. Let's there is two step. One step is 0.05 second, and another step is 0.1 second. So let us simulate this system within 0.2 second. Now run this simulation. Oh my god, I have got a error. What is the error? This error caused that the fees buck fuzzy logic controller, there is no buck fees. It is not finding any buck fees file. Sorry, fuzzy logic file. So why this happened? Because in our workplace there is no fuzzy logic file. So you have to generate a fuzzy logic file. How? So this was our fuzzy logic designer block. Here we designed all of this thing, and now in the file we have to export to workspace, and save the name bugfish. Okay, now you can see, you can close it now. Very nice. Now this is the bugfish, and this is a Mamdani fuzzy type object. Okay, so now we have got our fuzzy logic object, and there is bugfish named here, and if we run this, we should get a good result. But first of all, we have to please please note that I am changing this gain value to 1. I know this gain should be 3, but changing it 1, what will happen? I need to see this. So this is the gain, and we want to see, first of all, this is our input voltage. I'm writing it, input voltage. The second is output current, and sorry, this is third is output voltage. Sorry, output voltage. Second is output current. This is output current. Okay, and first is input voltage, and fourth is the output from the gain block. So I am saying it from gain block. Okay, now simulate it. I think it will take some time. Time is a valuable thing that we don't have, so let me skip this. So the simulation is over. Here, if you can see, input voltage is 12 volt up till 0.5 second, and when simulation goes to 0.1 second, output current goes from 0.5 ampere to 10 ampere. So here, if we zoom it, we can see that the output voltage is not perfect 5 volt. It is 5.5 volt or so. This is 5.5 volt, close to 5.5 volt. So this is not the desired value that I want. And also error. Here error is close to 0, if you can see. But here error is not 0. This problem. So what I did, I tuned this value, this gain blocks value I have tuned, and let us take 10, and see what will happen. Okay, so start the simulation again, pause it. So after setting the value of gain 10, we can see that output voltage gives a better performance. Here the error is 0 and output voltage is close to 5 volt, very close to 5 volt. So we can see that uh, it has tuned good. So what is the rule of tuning this gain parameter? So you need to see what is the error, what is the value of error. If error is within range of 0 plus 1 to minus 1, then your tuning is okay. Mostly the error should be close to 0. But if the error somehow goes beyond plus 1 to minus 1, then there is a problem and you have to change your gain parameter to reduce the error uh, within plus 1 to minus 1 limit. Okay, so 10 is good. The funny thing is I didn't use 10 previously. I used up to 3, but 10 gives a good result, so I will keep this. Now you can see that this fuzzy logic system has been done thoroughly. Now we will compare it with a PID controller. Now let's start a PID controller. Let's start a new file, and here there is a PID controller. Okay, so take this, copy this and paste here. Delete this and this. So everything is similar, only this block, this PID block is changed, and we used a discrete PID controller. Sample time is -1 inherited, and proportional gain is 0.5 and 10. Okay, now let us change this proportional gain. This is the best gain I have found. Now let's think that we don't know it. So how do you tune your PID controller? First of all, make the integral gain 0 and give as much as proportional gain you do want, like 10 or 100 or 1000. Who cares? Give 1000. Now we have to simulate it until let's give it a time. This is point this skip to 0.5. This is no, not 0.5, this is 0.1. This is 0.2 and all 0.3. Now run this. So observe the voltage. This is voltage. This is our step input voltage, and this is step output current, and this is our output voltage. This should be close to 5 volt. But observe that if this is oscillatory, yes, this is oscillatory. So good news. Is this is oscillatory? Yes, this is oscillatory. So good news. So if this is oscillatory, then we can use integral controller. But for high value, high value, this will be oscillatory. You need to find out the lowest oscillatory value, and see that the this is the error. See that the error should be close to the error should be close to 1, 0 to 1, because this error is giving the duty cycle. Okay, so this error, the output of the PID is going to the duty cycle block, so this should be 0 to 1, but here the output is 1000, so it's not good. Let's reduce it to 200 again to the simulation and find out that what is the output of the PID block. So the PID block is very high, 20, so that's not good, and there is a lots of uh, the amount of oscillation, or the amplitude of the oscillation is high. This should be very low. Okay, so you should further reduce it. So another 10. Now observe it again. Observe the error. The error is 5, so you have to reduce further. So reduce further and 10, half 5. But it's not good. As you can see, there is a lot of oscillation, so you have to reduce more than that. So 5, you should use 1. It is very much okay, but there is a lots of ripple here, so give our desired 0.5 and see what will happen here. It's good, eh? It's good actually, yeah. But see, we need to keep the voltage, output voltage, constant to 5 volt. But what is this? What is the voltage here? This is not 5 volt, this is 4.3 volt. So it's not actually tuned, and there is steady state error. Okay, because this is steady state and there is error, and also it doesn't go to 5 volt here, there is steady state. Okay, so the steady state occurs because there is no integral term. So now let's start the integral term tuning. So there the integral term is 0. Now start from very low value, like 0.5. It's up to you. You will find the actual most appropriate value after some tuning, some times of tuning. So this is not good. There is a lots of ripple and there is steady state error. So let's double it, 1. Okay, so okay, there is also steady state error, but here is steady error reduced, here also reduced, but there is also steady state error. So give it to 5. see that this is the steady state error is reducing here. As you can see, error is reducing, so we are on right track. We have to increase the integral gain further. So give this value 10. If you give this value 10, so now you can see the steady state error has become very close to 5 volts, so error is very low. So we can say the controller is tuned. I'm not saying the controller is tuned appropriately. You can pass your time with some music to find out the actual value of tuning. You can use your whole night to do the tuning. It's very romantic, I know, but this is what this is. I will use it for comparison with the fuzzy logic controller, but I'm saying there is more room to make better tuning. So let us close this. I have made this file. This is the two simulation file. Upper is the fuzzy logic simulation, and lower is the PID controller simulation, and the output of these two is given to scope, and we will see the output and compare it. First is fuzzy and second is PID. So let's start it, and it is running, and let's push it. Now we are pushed. So this is the output of the simulation. The yellow color is output from fuzzy, and the blue is from PI controller. Now you can see what is smart. Of course fuzzy is smart, and what is disgusting, PID is disgusting. Okay, so and PI also needs a lots of time to reach the steady state, whereas fuzzy is very quick to find out the steady state point. And here we can see PI has a great ripple, and fuzzy is very smart. And this is also so we have seen how to simulate a buck converter closed loop control system using fuzzy and PI controller, and we have compared their output, and conclude that fuzzy is better of than two. Thank you everyone. Goodbye.